Welcome to our work, Robust Test-time Adaptation in Dynamical Scenarios. First, let's provide a quick summary of our work. Our work proposed a novel and practical setup called Practical Test-time Adaptation, which considers distribution change and correlative sampling at test time simultaneously. To address the challenges of PTTA, we introduced the Robust Test-time Adaptation method, which incorporates robust statistics estimation, category balance sampling, and a time-aware strategy. Through extensive experiments, we evaluate rota on common test-time adaptation benchmarks, including CVPR-10C, CVPR-100C, and DomainNet, and the rota obtains 5.9%, 5.5%, and 2.2% performance gain on them respectively. Now, let's delve into the details. As we know that when training data and test data come from the same distribution, deep learning always achieves excellent performance. However, when training data and test data come from different distributions, the performance always drops significantly. In real-world, distribution shifts exist everywhere. The following figure shows a simple example that training data comes from a sunny day, but test data comes from night, snowy, foggy, and rainy days. Adapting deep models to new domains becomes crucial in such scenarios. Recently, test-time adaptation has attracted lots of studies. It attempts to adjust the distribution shift during the inference stage. Here is a normal workflow of TTA methods. After training, the pre-trained model will be adapted online by a test stream without access to source data. It makes predictions for current test sample and updates itself for future at the same time. Existing TTA setup makes some assumptions on the test stream. For example, fully TTA and continual TTA assume that the test stream is randomly drawn from a fixed or a continually changing data distribution respectively. Non-IID TTA considers the correlative sample test stream from a fixed data distribution. However, these assumptions are often broken in real-world applications. For example, the following figure demonstrates the scenarios of autonomous driving. We can clearly see that test samples are highly correlated over time, and the distribution changes as the surrounding environment changes in weather, location, or other factors. Based on above analysis, we propose a more practical test-time adaptation setup, where distribution change and correlative sampling occur simultaneously. And for short, we call it PTTA. There are three challenges under PTTA. Firstly, the correlation among test samples causes incorrect estimation in batch normalization statistics. Secondly, easily or quickly overfit to the local distribution observed in short period. Finally, error gradients accumulate when the distribution changes continually. We formulate PTTA as given a pre-trained model on source domain, we aim to adapt the model on a stream of unlabeled test samples, while test batches are correlated samples from distribution p-test, and the p-test changes as p0, p1 continually. Here is the framework of our proposed robust test-time adaptation method. The menu consists of three components: robust batch normalization, category balanced memory bank, and robust training strategies. The correlation among test samples xt at time t leads to a deviation between the observed distribution and the true test distribution. Directly adapting on the observed distribution leads to local overfitting. So we chose to maintain a category balanced memory bank to capture a robust snapshot of the current test distribution. Firstly, the balance among categories is guaranteed by distributing the capacity of the memory bank equally to each category, and the samples in major class will be replaced first. Please refer to line 5 to 9 in algorithm 1 for more details. Secondly, due to the continually changing test distribution, old samples in memory bank are limited in value and could even impair the ability of the model to adapt to the current distribution. And the samples of high uncertainty always produce erroneous gradient information that can hinder the model adaptation. So we design a heuristic score of timeliness and uncertainty as the following equation. High correlation among the test batch also makes the widely used test time Pn invalid. So we design a robust batch normalization. It maintains a group of global statistics from the memory bank as the following equation and adopts it for inference directly. When turned to updating, we notice that too old or unreliable instances still have opportunity to stay in memory, since keeping the category balance is assigned the top priority. Meanwhile, error accumulation caused by the distribution change also makes the traditional approaches like pseudo-labeling and the entropy minimization unworkable. So we turn to the robust unsupervised learning method, teacher-student model, and propose a timeliness reweighting strategy. At time t, after making predictions for a batch of test sample with the teacher model and updating the memory bank, we will update the student model by the following objective, and then update the teacher model by exponential moving average. In addition, for the sake of time efficiency and stability, only a 5 parameters in RBN are changed during adaptation. Here is the classification error on CVPR-10C and CVPR-100C while continually adapting to different corruptions at the highest severity 5 with correlative sample test streams. We can see that ROTA achieves the best performance compared to previous method. In more detail, ROTA has a significant performance gain to the second best method that 5.9% improvement on CVPR-10C and 5.5% improvement on CVPR-100C respectively, verifying the effectiveness of ROTA to adapt the model on the PTTA. More detailed and insightful analysis, please refer to the main paper. We conduct experiments on 10 different sequences of changes on CVPR-10C and CVPR-100C with independently and correlatively sampled test streams respectively. As shown in the figure, no matter what kind of setup, ROTA can achieve excellent results. We also vary the value of delta and the batch size on CVPR-100C. Excellent and stable results prove the stability and effectiveness of ROTA. In this work, we propose a more practical setup called practical test-time adaptation and launch a robust test-time adaptation method to address the challenges on the PTTA. Excellent performance validates the effectiveness of ROTA. We hope this work will pave the way for thinking about adapting models into real-world applications by test-time adaptation algorithms. Thank you for your attention. For more detail, please refer to the following links. If you have any questions, please feel free to contact me via email.